Hello and welcome. I want you to find a quiet place. Perhaps you're sitting in a comfortable chair or lying down ready for rest. Let the sounds of your world fade just for a little while. Let your breathing slow down. We are going to take a journey together, not across the land or the sea, but out far out into the quiet, deep ocean of space. There in that perfect darkness travelers move. They are silent, they are ancient, and most of all they are lonely. They move for millions, sometimes billions of years, drifting in the vast emptiness between the stars. We have only just begun to notice them. One of these travelers has captured our attention. It came from an unimaginable distance, from the direction of a star we do not know, from a home we cannot see. We gave it a name, 3 Atlas. The I in its name means interstellar. It is a visitor, a piece of another solar system wandering through our own. For months we watched it. It was a faint speck of light moving predictably quietly. It was a small, dark, cold object. It was, we thought, just a rock. An ancient frozen rock, perhaps covered in dark organic dust. It passed the orbit of Mars, then Earth, then Venus, falling faster and faster toward our sun. We tracked it. We studied its faint light. It was interesting, yes, but it was behaving as expected. And then it vanished. For weeks it was lost to us, hidden in the blinding glare of our own star. It made its closest pass by the sun, whipped around that massive furnace of gravity and light, and began its long journey back into the dark from which it came. We waited. Telescopes on Earth and in orbit turned their eyes to the patch of sky where it was predicted to reappear. We expected to see the same object, the same quiet, dark, simple traveller now moving away from us. But that is not what we saw. On November 10th, 2025, the images began to arrive. The Virtual Telescope Project, a network of eyes strung across our planet, captured the first clear view of 3I Atlas after its journey around the Sun, and it was no longer the same. The object that went in was not the object that came out. The new images are stunning, they are shocking. Before 3I Atlas was just a dot, a nucleus with maybe a very faint fuzzy cloud around it. Now it is magnificent. The new images show a long, brilliant and complex tail streaming away from it. This is not the simple tail of dust we might have expected. This is an ion tail, a tail made of glowing, superheated gas caught by the sun's magnetic wind and pushed directly away from the sun. It is intricate, it is filled with knots and streamers and jets. It is alive. This traveller, which had been silent for perhaps 1 billion years, has suddenly impossibly woken up. This is the impossible part. This is what has scientists and astronomers all over the world scrambling, confused and excited, because this should not happen. Think of a comet. We call them dirty snowballs. They are chunks of ice and rock left over from the birth of a solar system. For all of their lives, they are frozen solid deep in the cold. When they fall toward a star, the ice begins to warm up. It doesn't melt into water, it turns directly into a gas. This gas creates the fuzzy cloud called a coma, and it creates the beautiful tails that we see. But here is the crucial part. This is a gradual process. A comet that has enough ice to produce a magnificent tail after it passes, the sun should have also been producing a magnificent tail on its way in. The heating process is symmetrical. It warms up, it gets bright. It loops the sun. It cools down, it gets dim. 3I Atlas did not do this. It came in like a quiet, dormant asteroid. It is leaving like a spectacular active comet. The visitor has transformed. The pilgrim has changed its robes. It's as if a simple grey stone was thrown into a fire and it emerged as a diamond. It suggests that the object we are looking at now is fundamentally different from the one we were looking at just a few weeks ago. And so we are left with a profound and thrilling mystery. A something happened in those weeks when 3I Atlas was hidden from our view, lost in the sun's bright light. That period when we were blind was the moment of its transformation. What was it? What could have happened? Did it break apart? Perhaps the immense gravity of the sun and its intense heat was just too much. Perhaps the object cracked. Perhaps it shattered like an ice cube dropped in hot water. If it did, new surfaces, fresh ancient ice buried deep inside for billions of years, would have been exposed to the sun for the very first time. This new ice would have vaporized with incredible explosive force, creating the sudden brilliant tail we see now. Or did it collide with something? It's unlikely but not impossible. A small unknown fragment of rock also orbiting the sun could have struck it. Or is it something new? Is the chemistry of this interstellar object so alien, so different from our own comets that it reacts to the sun in a way we have never seen before? Did the sun's radiation trigger a chemical reaction on its surface? Something that ignited it? We do not know. All we know is that we were watching one thing and now we are watching another. The traveller has a secret. It carried a message from its home star hidden deep inside, and our sun just unlocked it. This is not a story from a textbook. This is not ancient history. This is happening right now. As you listen to these words, telescopes are staring at 3 Artem Atlas. Data is pouring in. Scientists are debating right now what it all means. We are all together witnesses to an impossible transformation. And that is where you come in. This is a shared moment of discovery. What do you think happened to it? What does this mystery make you feel? Let me know in the comments below. If you are as fascinated and as awed by this as I am, please consider liking or sharing this story. It helps this community grow and it lets us explore these great beautiful mysteries together. Because this is just the beginning. The traveller has finally woken up, and now we must learn to understand what it is trying to say. The astronomical community was holding its breath. After the weeks of baffling vibrant green signals and the strange metallic chemistry 3 Atlas had shown on its approach, it was finally time for its ultimate test. This moment, which we call perihelion, is the point of closest approach to the Sun. It is a trial by fire, a moment of maximum heat and maximum gravitational stress. For 3I Atlas, this fiery checkpoint occurred on October 30th, 25, and then just as the main event began, the object vanished. This wasn't a surprise, it was an inevitability. From our vantage point on Earth, 3 Atlas slipped behind the Sun, disappearing into the blinding glare. We entered a blind phase. For a time, our powerful ground-based telescopes, the great eyes on our planet's mountains, were rendered useless, overwhelmed by the light of our own star. But out of sight does not mean unwatched. Even as we were blinded, our tireless robotic sentinels in space kept their watch. The SOHO Solar and Heliospheric Observatory and the Stereo spacecraft, which are designed to stare at the Sun, were perfectly placed. They became our only connection to 3I Atlas as it endured the most violent part of its journey. We had to wait. We waited through the first few days of November. Then around November 5th, the first reports trickled in. Observers specializing in hunting objects in the dawn twilight began to just barely pick it up, a faint smudge fighting against the morning glow. The data was noisy, uncertain. But by November 10th, 3 Atlas had moved far enough from the Sun's glare to be seen clearly in the dark. And that is when the global astronomy community collectively gasped. It had a tail, a massive, brilliant, sprawling tail. This was the central mystery. Where did this come from? We had watched this object for months. It had jets, it had a green glow, but it did not have this. It looked like a quiet, rocky visitor. It went behind the Sun and came out transformed. It looked for all the world like a classic, magnificent comet. The immediate theories were sensational. Did the Sun's intense heat blast off a rocky outer crust, exposing a core of hidden ice that was now vaporizing? Did the object break apart, releasing a massive cloud of new material? The truth, as it so often is in science, was both simpler and far more elegant. It wasn't a problem of physics as much as it was a problem of perspective. The core explanation, the one that unlocked the entire puzzle, is this. The tail didn't suddenly appear. The tail was almost certainly there all along, we just couldn't see it. This is what astronomers now call the geometry problem. It all comes down to our specific point of view, our line of sight from Earth as we and the comet move through space. Let's use a simple metaphor. Imagine you are driving at night on a perfectly straight dark road. You are directly behind another car. You can see its red taillights clearly, but you have no idea if its headlights are on. The car itself, the coma in our analogy, is completely blocking your view of the beams streaming forward from it. Now imagine that car takes a wide curving exit ramp. As it turns its angle relative to you changes, you're no longer directly behind it. You're off to its side, and for the first time you see it a brilliant white cone of light from its headlights slicing through the darkness. The headlights were never off, your angle just changed, opening up the view. This is precisely what happened with 3 Atlas. On its journey towards the Sun, its dust tail, which is made of small particles gently pushed away from the Sun by the pressure of sunlight itself, was streaming almost directly away from us back along its path. We were flying in formation with it looking straight down the barrel of its tail. This effect, called foreshortening, meant the entire tail was compressed into a tiny point from our perspective, and it was completely hidden behind the much brighter glowing coma, the central cloud of the object itself. We were looking at the back of the car, but after 3 or so, Atlas whipped around the Sun at perihelion, its trajectory changed dramatically relative to ours. It was no longer heading inward with us, it was now heading outward on its long journey back to interstellar space. Earth continued on its own orbit, and the car, our cosmic visitor, began to make its turn on the exit ramp. Day by day, as 3i, Atlas and Earth moved along our separate paths, the viewing angle, what astronomers call the phase angle, began to open up. That hidden tail rotated into our view. What we witnessed with such shock on November 10th was not a new creation. It was the grand revelation of a tail that had been hidden in plain sight for months. This theory sounds neat, but science demands proof. If the tail was always there, is there any evidence? Absolutely, and it comes from our most powerful tools. Before 3 Atlas disappeared behind the sun, astronomers using the Hubble Space Telescope and the Gemini Observatory did report detecting an extremely faint, difficult-to-see tail structure. At the time, the observations were complex. The tail was so faint and the angle was so poor that the data was secondary to the comet's other stranger behaviours like its green glow and nickel jets. But those early tentative detections are the smoking gun. They proved that the structure existed before perihelion. It just took the post-perihelion change in geometry for that tail to be fully and gloriously unveiled for all of us to see. So the mystery of the appearing tail was solved. It wasn't a sudden magical transformation, but a beautiful, predictable trick of cosmic alignment. But this solution only opened the door to an even deeper question. Now that we could see it, what was this tail made of? A comet's tail is its biography written in dust and gas. It is a flowing particle-for-particle record of what the object is shedding, what it's really made of, and exactly what happened to it during that fiery passage past the sun. So what does the specific structure of this newly visible tail finally tell us about the true strange nature of this visitor from the stars? We have followed this object's path, a line drawn through our solar system from an origin we can barely imagine. We've calculated its trajectory and confirmed that it is not one of ours. It is a true interstellar visitor. Now we move from the abstract world of orbital mechanics to the physical reality of the object itself. We are no longer just asking where did it come from, we are asking what is it? The story it tells is not simple. It's written in a language of light, gas and motion, and the most revealing chapter, the one that truly defined its character, began with a single image captured on November 10th. Let's try to visualize this moment. For weeks, astronomers had been tracking a faint point of light. They knew its speed, they knew its path, but on this day the data that came back from the world's most powerful telescopes wasn't just numbers on a screen, it was a photograph. And this photograph was the object's first true detailed portrait. Imagine hearing stories about a traveller from a faraway land and then finally seeing them in person, only to find they are not at all what you expected. The image was stunning. The term scientists used to describe it was complex morphology. This sounds like a very dry-back and technical phrase, but in the astronomical community it's a way of saying, this is strange, this is chaotic, and this is beautiful. Morphology is simply the scientific word for an object's shape and its structure, and complex was perhaps an understatement. A normal comet, if such a thing exists, often shows two distinct tails. There is usually a broad, pale and gently curved tail made of dust and metal. Then there is a fainter, straighter and narrower tail made of gas. This object was different. Its gas tail, its ion tail, was the star of the show, blazing with an eerie, unmistakable blue-green light. And it was not a single neat streamer. It looked almost shredded. The image revealed multiple distinct streamers flowing away from the comet's head. Think of a bright ribbon that has been torn into several long strips, all fluttering together in a powerful invisible wind. There were bright knots, denser clumps and darker gaps between these streamers, proving that the process creating them was not smooth but gusty and uneven. Furthermore, the entire structure wasn't perfectly straight. It showed a noticeable curvature, a distinct bend. This was also a profound puzzle. Ion tails are supposed to be a perfect cosmic weather vane. They are pushed directly away from the sun by the solar wind, so they should be straight. Seeing a bend, seeing the tail look tangled, was a major clue that something remarkable was happening. What could cause this? Scientists immediately focused on two main possibilities, which were likely both happening at once. The first theory was that the source itself, the comet's solid heart, its nucleus, was complicated. It wasn't just a smooth, uniform ball of ice, evenly steaming like a piece of dry ice in water. It must be a lumpy, uneven body rotating as it flew. As it spins, different active regions on its surface, think of them as massive icy geysers, are exposed to the full force of the sunlight. These jets would then fire off huge plumes of gas and dust in specific directions. The combination of multiple jets firing at different times and in different directions as the nucleus tumbles through space would absolutely create a tail that looks like a set of tangled, complex streamers. The second possibility was that the environment the comet was flying through was to blame. The wind in space is the solar wind, and it is not a steady, gentle breeze. It's a turbulent, high-speed river of charged particles flowing from the Sun. It has fast streams and slow streams, gusts and lulls, and complex magnetic fields tangled within it. The comet was flying through this invisible, chaotic weather. The curved and complex tail streamers may have been a visible record of this interaction, like seeing the path of a miniature tornado picked up in dust. The image from November 10th was a snapshot of this incredible chaotic dance, a complex spinning nucleus firing off jets of its own material into a powerful turbulent wind from our Sun. This vivid, complex tail is the comet's real-time broadcast. It's telling us in glowing colour what it's made of and what it's experiencing. To read that message, we have to understand the basic science of how this tail is even created. It's a two-part story because comets have two different tails. The first tail, which this object also means, is the dust tail. This one is simple. The Sun's heat boils off gas from the comet, and this gas drags tiny particles of dust and rock with it. These solid particles are then gently pushed by the pressure of sunlight itself, the same way a breeze can push a sailboat. This tail is heavy and slow to react, so it tends to lag behind the comet, often forming a broad, curved and pale yellow tail. It shines only because it's reflecting sunlight. But the second tail, the one that was so spectacular on this object, is the ion tail. It is a completely different beast formed by a much more violent process. It's not smoke, it's not steam, it is a whisper, thin, glowing plasma. Its creation is a beautiful multi-step process. Step 1. The source. It all starts with the icy nucleus. As it warms, ice is like water, and in this case a large amount of carbon monoxide turned directly from a solid into a gas. This process is called sublimation. This gas forms a huge temporary atmosphere around the nucleus called the coma, which can grow to be larger than a planet. Step 2. The Sun's other power. This is the magic ingredient. The Sun doesn't just send out heat and visible light, it bombards the entire solar system with invisible high-energy ultraviolet radiation. This UV light is like a microscopic bullet. When one of these high-energy photons hits a neutral gas molecule in the coma, let's say a carbon monoxide molecule, it has enough energy to knock an electron completely off that molecule. Think of an electron as a tiny, negatively charged cloak. As long as the molecule wears it, it's electrically neutral. But when the ultraviolet light rips that cloak away, the molecule is left exposed. It now has a tiny positive electrical charge. It has become an ion. Step 3. The solar wind. This new charged particle is now fundamentally different. A neutral gas molecule is like a speck of dust just drifting, but a charged ion is like a tiny magnet, and it has just been born into a world filled with powerful magnetic forces. This world is dominated by the solar wind. This is a non-stop high-velocity stream of charged particles, mostly protons and electrons, that the Sun ejects from its atmosphere in all directions. It travels at truly incredible speeds, carrying the Sun's magnetic field along with it. When the comet's new carbon monoxide ion meets this magnetic solar wind, it is instantly captured. The solar wind acts like a cosmic broom, sweeping all of these newly created ions up and throwing them backwards straight away from the Sun. This is the ion tail. It is a stream of the comet's own material, first electrified by the Sun's radiation and then blown away by the Sun's wind. This is why the ion tail always points directly away from the Sun, no matter which direction the comet itself is travelling. It is a perfect compass needle pointing away from the solar system's powerful centre. Step 4. The colour. So why that stunning blue-green glow? This isn't reflected sunlight. The ion tail creates its own light. This process is called fluorescence. The carbon monoxide ions, having been energized by sunlight, are in an excited state. They don't want to stay that way. To relax, they must release that extra energy, and they do so by spitting out a particle of light, a photon. And it just so happens that carbon monoxide ions release this energy at very specific colours, the exact wavelengths of light that our eyes see as blue and green. So when we looked at that complex, bright green-blue tail, we were not just seeing a pretty shape. We were in effect looking at a chemical fingerprint. We were watching in real time as carbon monoxide gas from another solar system was being ionized by our Sun and carried away by our solar wind. Observing from Earth, even with the best telescopes, is like watching a ship sail toward a massive storm on the horizon. You see it go in, but you can't see what's happening to it inside the storm. For this comet, the storm was its perihelion, its moment of closest, most violent approach to the Sun. At that close range, the Sun's gravitational pull is immense, trying to tear the comet apart with tidal forces. The heat is scorching, vaporizing tons of material every single second. Many comets do not survive this. They are called sun grazers, and they very often simply vanish, either breaking into millions of tiny invisible pieces or completely vaporizing into nothing. We needed eyes that could look directly into that storm. These were our space-based solar observatories, spacecraft like SOHO, the Solar and Heliospheric Observatory. These spacecraft are our solar sentinels. Their job is to stare at the sun's superheated outer atmosphere, the corona. In doing so, they are perfectly placed to see any object that dares to fly that close. As the comet plunged toward the sun, it entered SOHO's field of view. The world watched. Would it fragment? Would it vanish? The data streamed back to Earth. And the first major conclusion was a shout of triumph. It survived. It appeared on the other side of the sun, bruised and battered perhaps, but demonstrably whole. It had not disintegrated. This was a crucial finding. It told us that the nucleus was strong. It was not just a loose fluff ball of ice and dust, but a cohesive solid body strong enough to withstand the most extreme forces our solar system could throw at it. But the data from SOHO and its sibling spacecraft revealed a second, even more startling conclusion. It was continuously and intensely active. It didn't just passively endure the passage. The entire time it was in SOHO's view, it was furiously active. The data showed it brightening and flaring, releasing enormous visible bursts of gas and dust as it flew. It was fighting back against the sun's onslaught. This sustained, powerful activity was the sign of a body that was incredibly rich in volatile ices. This wasn't just a surface layer burning off. The heat was triggering deep, powerful jets from within its core. It put on a show that rivaled some of the most active comets ever recorded, and it did this throughout its entire solar passage. This was not a quiet guest, it was a roaring, dynamic engine. So let's step back and look at the portrait we've just painted. This is part 3, reading the data. And the data told a consistent, powerful and dramatic story. It began with the image from November 10th. That photograph with its complex morphology, its multiple curved and tangled streamers was our first major clue. It told us we were dealing with a complex object either firing off chaotic jets from a spinning nucleus or being violently twisted by a turbulent solar wind, or most likely both. We then learned why it was glowing. We learned the science of the ion tail. We understood that the stunning blue-green colour was not a reflection, but a chemical fingerprint. It was the specific light of carbon monoxide ions first created by solar radiation and then swept away by the solar wind. This told us what it was made of. And finally our eyes in space confirmed its strength. It faced the full destructive fury of the sun at perihelion, and it did not break. It held together. And it didn't just survive, it thrived. It was furiously, continuously active, proving it was a body packed to the core, with volatile ices erupting in a spectacular sustained display. Every single data point, from the shape of its tail to the colour of its light to its behaviour around our sun, pointed to one unified conclusion. This was an object from another star, and it was one of the most dynamic, active and chemically rich comets humanity had ever had the privilege to witness. It was not a quiet dead rock. It was alive with cosmic energy. Continuing the script, Part 4, The Brightness Anomaly, a physical puzzle as 3i Atlas began its journey inward closer to the warmth of our sun. We watched. All of us watched. Astronomers pointed their telescopes and the rest of us watched the headlines. We were watching a visitor from an unknown place, and we expected it to behave according to the rules we knew. We have rules for comets. We have watched thousands of them. We know how they work. They are for the most part predictable celestial travellers. They are dirty snowballs that get a little fuzzy as the sun heats them. We know the math. We know the script they are supposed to follow, but 3i Atlas did not know our script. It refused to follow the rules, and the very first rule it broke so completely, so spectacularly that it forced us to reconsider everything. This was the first great puzzle, its light. The new problem wasn't just that it was bright, the problem was the rate at which it was getting bright. It was its terrifying, impossible acceleration of brightness. Let's put this in perspective. Imagine you are standing on a dark road and you see the single headlight of a motorcycle in the far distance. As it gets closer, it gets brighter, and it follows a simple physical law. If it cuts its distance to you in half, its headlight becomes 4 times brighter. This is the inverse square law, a fundamental rule of light. A normal comet is a little more complex. It's not just reflecting light, it's also creating its own cloud of gas and dust which also catches the sunlight. So a normal well-behaved comet from our own solar system, say, from the Oort cloud, doesn't just get 4 times brighter. As it cuts its distance to the sun in half its cloud of gas and dust, its coma expands and it might get 8 or perhaps 16 times brighter. This is the standard model. This is the behaviour we expected. It follows a mathematical relationship that scientists describe using the object's distance, which they call r. They say the brightness is proportional to the distance, or r, to the power of -3 or -4. This is just our baseline, our normal. Atlas did not follow this rule. It didn't even come close. As 3i Atlas cut its distance to the Sun in half, it did not get 16 times brighter. It got 181 times brighter. Let this sink in. It is a difference so vast it borders on the absurd. It is the difference between someone turning on a reading lamp and someone setting off an explosion. It is the difference between a gentle melt and a catastrophic detonation. The data reported by researchers Zhang and Batams showed its brightness was proportional to its distance to the power of -7.5. This number 7.5 was a shock. It was a signal flare telling the entire astronomical community that this object was not a simple inert dirty snowball. It was something else. It was alive. What in the vastness of space could cause such a thing? What could possibly fuel an engine that burns this hot, this fast? The hunt for an explanation began, and it split into two main camps, both of which pointed to an object with a very strange, very exotic nature. The first and perhaps most popular theory was the super volatile explanation. We call water ice a volatile material. It stays solid when it's very cold, but as you warm it up, it turns to gas steam. Our comets are full of water ice, but water needs to get relatively close to the Sun inside the orbit of Mars, say, to start boiling and sublimating into gas in a significant way. But there are other substances in the universe, materials that are far, far more volatile than water. Things like frozen nitrogen or frozen methane, or most commonly frozen carbon monoxide. We call these super volatiles. Here on Earth, carbon monoxide is a gas. But in the deep frozen void of interstellar space, where temperatures are just a few degrees above absolute zero, carbon monoxide freezes solid. It becomes a kind of ice. Now imagine a comet that isn't just made of water ice, but is packed with this solid carbon monoxide. Water ice is like a block of ice on a warm day. It melts, it drips, it's a slow process. Solid carbon monoxide is like a block of dry ice on a hot stove. It doesn't melt, it explodes. It sublimates with incredible violence. The moment the faint distant sunlight touched 3i Atlas, these super volatiles, which had been frozen solid for perhaps millions or billions of years, began to boil. But this wasn't the gentle boiling of a kettle. It was the explosive flash boiling of a substance that cannot tolerate even the slightest warmth. This would explain the 7.5 to the power of -7.5 behaviour. It wasn't just the amount of sunlight hitting it, it was that any sunlight was enough to trigger a runaway reaction, releasing enormous pressurized plumes of gas from deep within its body. The second theory was about its structure. This theory suggested that 3i Atlas was fluffy. This word sounds gentle, but in a cosmic sense it's revolutionary. We tend to think of asteroids and comets as solid, dense rocks of ice and dust. But what if 3i Atlas wasn't solid? What if it was an incredibly light, incredibly porous object? Imagine a giant cosmic dust bunny, a fragile collection of ice-coated dust grains barely held together by gravity. Why would this make it brighter? Because a fluffy object has a massive surface area. Think of it this way. A solid block of wood is hard to light. It burns slowly from the outside in. But if you take that same block of wood and shave it into sawdust, the fluffy pile of sawdust is incredibly flammable. A single spark can make it flash. If 3i Atlas was this fluffy heat from the Sun wouldn't just warm its surface, the sunlight could penetrate deep inside, finding hidden pockets of ice. And as those ices turned to gas, they wouldn't just vent gently. They would tear the fragile, fluffy structure apart, exposing new fresh ices, which would then explode in a chain reaction. This fluffy model, or the super volatile model, or perhaps some combination of the two, was the only way we could begin to explain that stunning 181-fold increase in brightness. It was a creature from the cold dark, and it was screaming in the light. This intense activity led to another observation, one that caused a new round of confusion and excitement in the media. The headlines began to claim that 3i Atlas was changing colour. Reports said it was becoming greener than the Sun. This understandably captured the imagination. What did it mean? Was the comet physically painting itself green? Was it some strange alien property? The truth was not a physical change, but a spectral one. It wasn't a puzzle, but a powerful confirming clue. Here's what was truly happening. When we look at a normal quiet comet, most of the light we see is just sunlight. The sun's light is yellowish-white. The comet, a dirty snowball, reflects this yellowish-white light. So the comet looks yellowish-white. It's a simple mirror. But 3I Atlas was not a quiet comet. It was erupting. It was spewing a massive expanding cloud of gas into space, its new atmosphere, or coma. This gas was not just sitting there. It was being energized by the sun's radiation, a process called fluorescence. And when specific gases are energized, they don't just reflect light, they glow. They emit their own light at very specific colors. It turned out that the gas 3I Atlas was releasing in massive quantities contained chemicals like cyanogen, a molecule of carbon and nitrogen and diatomic carbon, 2 carbon atoms bonded together. And when sunlight hits these 2 specific gases, they glow with a brilliant, unmistakable greenish-blue light. This is the key. In the beginning, we saw both sources of light, the yellowish light reflected from the comet's nucleus and the greenish light from its glowing gas cloud. But 3I Atlas was brightening at that exponential rate of 5 r to the power of negative 7.5 rate. This meant its gas production was dominating everything. Soon the faint green glow of the gas became thousands, then tens of thousands of times brighter than the pale yellow light being reflected by the tiny hidden nucleus. When astronomers pointed their telescopes at it, the green signal from the gas completely overwhelmed the yellow signal from the reflection. The comet didn't turn green. The green simply took over. Imagine a campfire. You see the yellow-orange glow of the burning logs. This is the reflected light. But if you toss in a chemical, the flame itself might turn a brilliant vivid green. The logs are still there, still yellow-orange, but the gas is so bright that all you can see is green. This wasn't a color change, it was a revelation. The green color was the signature of its violent, explosive gas production. It was direct visual proof that the super volatile or fluffy theories were correct. This object was shedding gas at a rate we had never seen before. And this has consequences. An object cannot burn that brightly for long. It cannot shed that much of itself without paying a price. This intense explosive activity, this furious loss of mass, was a symptom of its own self-destruction. It was tearing itself apart. This furious activity, this screaming green light, was not a sign of strength. It was the beginning of the end. All of this gas, all of this dust, all of this lost material was being thrown out into space, and that in turn created the next puzzle. What was in that material? What was this alien messenger truly made of? In our journey so far, we have looked closely at the light from 3I Atlas. We've examined its chemical fingerprint, that strange and ghostly green glow. We've puzzled over the materials it seemed to be burning, the iron and nickel that felt so out of place, so much more like a piece of a planet than a simple ball of ice. But all of those were mysteries of substance. They were questions about what the object was made of. Now we turn to a different kind of mystery. A mystery not of composition, but of motion. It is a puzzle that in many ways is even more profound because it challenges the most fundamental rules we have. For centuries, our understanding of the cosmos has rested on a beautiful, unwavering foundation, the law of gravity. It is the most reliable narrator in the universe. Gravity dictates the dance of the planets, the gentle swing of a moon, the long sweeping, predictable arc of a comet falling toward the sun. We can write equations on a piece of paper, equations born from the minds of Newton and Einstein, and with them we can predict the future. We can tell you with breathtaking precision exactly where Jupiter will be in 100 years. We can tell you where a tiny icy visitor from the dark should be, down to the arc second. This certainty, this mathematical clockwork, is the bedrock of astrophysics. It is the cosmic metronome ticking away reliably, predictably. Until it isn't. As 3I Atlas raced towards the sun, astronomers did what they always do. They tracked it. Night after night, they measured its precise position against the background of fixed, distant stars. They fed these coordinates into their computers. The computers, running on the pure, clean logic of gravity, drew a line, an elegant curved path showing exactly where the comet should be at any given moment. But a new problem emerged. When astronomers pointed their telescopes to that precise calculated spot in the sky, 3I Atlas wasn't quite there. The discrepancy was tiny, almost imperceptibly small at first. A tiny lag, a tiny lead, but in the world of orbital mechanics, tiny is everything. A tiny error in calculation means your probe misses Mars. A tiny deviation in a comet's path means the comet is not listening only to gravity. It means something else is pushing it. This something else has a name. It is called non-gravitational acceleration. It is a simple, dry technical term, but it means something wonderfully dramatic. The object is acting on its own. It is accelerating or decelerating for reasons that gravity alone cannot explain. The cause of the push now. For most comets, this is not a mystery at all. In fact, we expect it. We call it the rocket effect. Imagine a comet as a giant, lumpy, spinning ball of ice, rock and dust. It has spent thousands, perhaps millions of years in the deep freeze of outer space. Now it falls toward the sun. As it warms up, the ice on its surface doesn't melt in the vacuum of space, it sublimates. It turns directly from a solid into a gas. This gas does not seep out gently. It erupts, it bursts from the surface in powerful jets like thousands of tiny chaotic geysers. If the comet were a perfect non-spinning sphere, heating uniformly, the jets would fire equally in all directions and nothing would happen. But a comet is a lumpy, irregular spinning potato. As it tumbles, one side gets more sunlight. That side fires off more jets. And if just by chance the back of the comet is more active than the front, all those jets of escaping gas create a gentle, persistent push. It is the exact same principle as a rocket engine, or even just letting go of an inflated balloon and watching it zip frantically around the room. The escaping gas provides thrust. This thrust is the non-gravitational acceleration. It's messy, it's chaotic, but it is a normal expected part of being a comet. So 3I Atlas was just being a normal gassy comet, right? It was pushing itself around with its own jets. Case closed. No, this is where puzzle number 2 truly begins. The problem wasn't that it was accelerating. The problem was how much it was accelerating. The push was strong. It was surprisingly significant, significantly strong. The shocking calculation. This is where the debate truly ignited. Scientists, including Avi Loeb and his colleagues, sat down to do the math. It's a straightforward calculation on paper to get this much push. The observed acceleration, you must be expelling this much material, the gas. They ran the numbers, and the answer that came back was staggering. To account for the powerful acceleration they measured, 3I Atlas would have to be shedding an enormous, almost unbelievable amount of its own mass. The estimates were shocking. The object would have needed to lose somewhere between 10 and 13% of its entire total mass, and it would have to do this in just 1 month. Let's pause and truly visualize what this means. Imagine a mountain. Now imagine that in 30 days, 1/10 of that entire mountain had to dissolve, vaporize, and shoot into space just to provide the push that was seen. This wasn't a gentle hiss of gas. This calculation implied a violent, rapid, self-destructive process. It was as if the object was tearing itself apart, vaporizing its own body to provide the thrust. This was not normal. This was not a standard comet. This figure 10% was so high that it immediately created a storm of scientific skepticism. The scientific debate. This is the beauty of the scientific process. It is a community built on debate and proof. An extraordinary claim that a comet was dissolving at a rate of 10% per month requires extraordinary evidence. And the counter-arguments came quickly. The skepticism focused on several key points. First, was the measurement of the acceleration itself reliable? Tracking a tiny fuzzy object millions of kilometers away is incredibly difficult. The data is noisy, full of tiny errors. Perhaps the computer models were wrong. Perhaps they were mistaking a small brief event for a long, powerful push. The team that made the measurements stood by their data. The statistical certainty, they said, was high. The object was without a doubt deviating from its gravitational path. Second, and this is the most important part, were the assumptions correct? That 10% figure is not a direct measurement. It is a calculation, and that calculation depends entirely on a few numbers that scientists had to guess. To find out how much mass was lost, you must first know 2 things. How fast is the gas shooting out? And most importantly, how big is the comet to begin with? We never knew. We never got a clear picture of the nucleus, the solid part of 3I Atlas. We could only estimate its mass based on how bright it was. If you assume the comet is very, very heavy, you need to expel an absolutely colossal amount of gas to push it. If you assume the comet is very, very small and light, then it's easier to push and you need less gas. The 10% number was a middle ground, but it rested on a foundation of educated guesses. The critics argued fairly that if the nucleus was much smaller than we thought, this whole mass crisis would disappear. But this led to the third and most profound part of the debate, the contradiction we could see. There was one piece of evidence that contradicted the 10% theory, and it was the most obvious one of all. We were watching it. If an object is truly losing 10 to 13% of its entire body mass in a single month, if it is violently sublimating, blasting a mountain's worth of material into space, you would expect to see it. You would expect the comet to get dramatically, spectacularly brighter as all that new gas and dust exploded into the sunlight. Or you would expect it to fade dramatically as the active nucleus essentially vanished, having burned itself out. You would expect its shape, its brightness, its coma to change night after night. But that is not what observers reported. The reports were baffling. They said the comet looked constant. It remained stable. Its brightness was not fluctuating wildly. It just sailed on, glowing its strange green, looking like a perfectly normal if slightly overactive comet. This was the core of puzzle number 2. It was a profound contradiction, a logical impasse. The math said one thing, catastrophic violent change. The visual observation said another, calm, boring stability. How can an object be simultaneously tearing itself apart and look completely unchanged? What we know for sure. So where does this leave us as we float here in the quiet, contemplating this green traveller? The debate continues, but we can hold on to a few solid truths. We can separate what we know from what we infer. Here is what we know for sure. Fact 1. The comet experienced non-gravitational acceleration. It was definitely measurably being pushed by something other than gravity. The math on this is secure. Fact 2. This push must have come from mass loss. To be pushed forward, it had to be throwing something backward. The rocket effect is the only viable physical explanation. Gas, dust and ice were leaving the comet. But the great unknown. The amount of mass that was lost. This remains the heart of the puzzle. Was it a gentle, normal amount of gas coming from a nucleus that was simply much smaller and lighter than we assumed? Or was it the catastrophic mountain dissolving in a month scenario that the raw calculations suggested? Science at this moment cannot definitively say. That 10% figure hangs in the air, a shocking, unproven but mathematically derived possibility. And so 3i Atlas presented us with two related wonderful mysteries. A chemical signature that looked like nothing we had ever seen, and a movement that implied a level of self-destruction that paradoxically we could not see happening. These puzzles, the colour and the acceleration, set the stage for the final act. Because as 3i Atlas began to move away from the sun, heading back into the cold dark void, it did one last thing. It gave us one final definitive and heartbreaking clue that would change the entire debate. It shattered. We are left with a fascinating puzzle, perhaps the most human part of the 3i Atlas story. It is a story of conflict not in the stars but in our own understanding. We have two very different portraits of this object. The first portrait is painted by the mathematicians and the physicists. It is based on the hard data of the comet's path. This portrait is dramatic. The calculations derived from that strange rocket effect pushing the comet off course are demanding. They insist that 3i Atlas must have been shedding an enormous amount of its own body. The numbers suggested a mass loss so extreme that the comet might have lost 10% of its entire self during that single fiery pass around our sun. This calculation paints a picture of a violent self-destructive event, a body tearing itself apart in the sea from the sun's heat. The second portrait is painted by the astronomers, the observers sitting at the telescopes. This portrait is strangely one of calm. When they looked at the photographs, when they measured the light, 3i Atlas looked fine. It was bright, yes. It was active. But it did not look like an object in its death throes. It didn't appear to be shattering into large pieces. Its bright central core, the coma, looked stable. This is the heart of the paradox. The numbers scream catastrophe while the pictures whisper all is well. How can both be true? How do we reconcile what we calculated with what we saw? The solution to this mystery is in not a failure of our science, but a beautiful lesson in humility, a reminder of what it truly means to observe the cosmos. The paradox dissolves when we look closer not at the comet, but at our own assumptions. First, we must ask, what were we expecting to see? When we hear a comet loses 10% of its mass, our minds conjure images of a car crash. We imagine huge visible chunks of rock and ice breaking off and flying away, a dramatic spray of debris. But the calculations were not measuring big visible boulders. The force pushing the comet was not from large explosions. It was from the gentle, persistent thrust of gas and dust. The vast majority of the mass 3E atlas lost was likely in a form that is completely invisible to our eyes and most of our telescopes. It was venting gases like water vapor, carbon dioxide, and carbon monoxide. These are transparent. You cannot see water vapor in the vacuum of space. The comet was hemorrhaging its lifeblood, but it was bleeding invisibly. It was like a colossal steam engine venting, but in the silence of space, this steam just dissipates unseen into the void. But what about the dust, you might ask? Comets are famously dusty. Indeed, 3I Atlas was incredibly dusty, but again, our intuition about dust on Earth misleads us. The material lost was not gravel. It was a fine powder of microscopic grains. As soon as these tiny grains were freed from the comet's incredibly weak gravity, they were immediately pushed away by the pressure of the sunlight itself. They didn't hang around the comet in a dense, easy-to-see cloud. They dispersed, scattering rapidly across millions of miles. It is the difference between seeing a bucket of sand piled high and trying to see that same bucket of sand after it has been scattered one grain at a time across an entire football field. The mass is still lost, but it becomes too thin, too diffuse to register as a breakup event. This brings us to the most important solution, the one that requires the most profound shift in perspective. The observation that the comet looked unchanged is in fact precisely what we should have expected. The calculation was a 10% loss of mass. Let us try to visualize what that actually means for a comet's size. Imagine 3Ards Atlas is a sphere of ice and rock roughly 3 kilometers wide or about 1.8 miles. A 10% loss of mass, if it was shed evenly from the surface, would only shrink its diameter from 3 kilometers down to about 2.7 kilometers. Now we must be very honest about our capabilities. We are on Earth looking through our atmosphere across billions of miles of intervening space at an object just a couple of kilometers wide. We cannot see the comet. That may sound strange, but it is the literal truth. We do not see the comet's solid body, the nucleus. It is a speck far too small to ever be resolved by any telescope on Earth. It is a single dot of light. What we see is not the comet itself, but the coma, the massive fuzzy cloud of gas and dust around it, illuminated by the sun. From our distant viewpoint, there is absolutely fundamentally no way to tell the difference between a 3-kilometer dot and a 2.7-kilometer dot. We are completely blind to that kind of change. So the comet could have shrunk, it could have lost a massive portion of its body, and from our vantage point we would simply never have known. The observation of no visible change is not a contradiction of the calculation. It is a confirmation of our own observational limits. But what about the reports that its tail vanished? Surely that's a sign of a change. This was one of the most baffling reports. For a time it seemed its dust tail had just disappeared, only to reappear later. This suggested something dramatic. The solution, however, was not one of physics but of geometry. It was an illusion on a simple trick of our perspective. As Earth moves in its orbit and the comet moves in its our viewing angle is constantly changing. What astronomers now believe happened is that for a short time Earth, the comet and its tail lined up almost perfectly. We were looking straight down the length of the tail. When you look at a long thin object, end on, it seems to disappear. It's like turning a sheet of paper to look at it perfectly from the edge. The paper is still there, but from that one angle, it becomes an almost invisible line. As our planets continued their dance, our viewing angle shifted, and the tail reappeared, revealing itself once more. It was never gone. So we find ourselves at a place of resolution. There is no paradox. The calculations are almost certainly correct in their essence. 3A Atlas did lose a significant, perhaps even extreme amount of its mass. The debate that remains is only about the exact amount. Was it moderate or was it the extreme 10%? And the observations were also correct. It did look unchanged. The solution is the quiet realization that the lack of visible dramatic change was predicted by the very limits of our technology. We were looking for a catastrophic explosion, but the comet was dissolving like a sugar cube in warm water, losing its substance bit by bit in a way that is fundamental but not explosive. The mystery was never in the comet itself. It was in our own expectations in the gap between what we can calculate and what we can truly see. Sometimes the greatest discoveries in science aren't the result of a meticulous decade-long plan. They are the result of pure spectacular luck. They happen when a perfectly normal Tuesday turns into the day you find a winning lottery ticket on the sidewalk. In the grand cosmic sense, this is what might have just happened with 3I Atlas. The universe, it seems, may have given us a gift of a chance encounter of astronomical proportions. Here is the exciting possibility as 3I Atlas was rounding the sun, burning bright and releasing its massive tail of gas and dust. 2 spacecraft may have flown right through that tail. These spacecraft were not there to see 3I Atlas. They were on entirely different missions focused on completely different parts of the solar system. The first is Hera, a mission by the European Space Agency, which is on its long journey to the Didymos binary asteroid system. The second is NASA's Europa Clipper, a flagship mission heading to Jupiter to study its icy moon Europa, searching for the ingredients of life. Neither mission's flight path was designed to intercept this interstellar visitor, and yet based on the calculations of 3 Atlas's orbit and the trajectory of its enormous tail, a team of scientists led by Grant and colleagues made a stunning prediction. They calculated that Hera was likely to pass through the outer regions of the object's tail sometime between October 25th and November 1st. Even more exciting was the prediction for Europa Clipper. The team calculated its encounter window to be between October the 30th and November 6th. This timing is absolutely critical. This was the exact same week that 3i Atlas was at perihelion, its closest, hottest and most violent point of approach to our Sun. This is when the object was at its most active, shedding the maximum amount of material into space. Clipper wouldn't have just flown through a faint wispy tail. It might have flown through the dense, freshly released core of the plasma and dust stream. What does this mean? It means we might have in situ data. This is the absolute gold standard for space science. In situ is a Latin term that simply means in the original place or locally. Almost everything we know about 3 Atlas so far comes from remote data. We use telescopes on Earth or in Earth's orbit to look at it from hundreds of millions of kilometers away. It's like trying to understand a volcano by watching its smoke plume from a neighboring country. You can learn a lot, but you can't know what the ash feels like or what the ground smells like. In situ data is the opposite. It's like sending a robotic probe to fly right through the smoke plume, dip a bottle into the ash cloud and grab a sample. It is the difference between looking and touching. If these spacecraft did fly through the tail, and if their instruments were on, they will have captured data that we could never ever get from Earth. Let's think about what these ships are carrying. They are packed with sophisticated scientific tools. A spacecraft like Europa Clipper, designed to study the environment of a moon, is built to taste the space around it. First, it has a magnetometer. This is an instrument that measures magnetic fields. We could find out if 3 Atlas's tail was creating its own magnetic disturbance, or how it was interacting with the Sun's magnetic field known as the solar wind. This tells us about the physics of the plasma itself. Second, it has plasma detectors and ion composition instruments. This is perhaps the most exciting part. These detectors are like the spacecraft's tongue. As it flies through the cloud of gas, it catches the individual atoms and molecules, the ions, and measures them. It can tell us exactly what those gases are. Not just there is gas, but there is this much argon, this much neon, this much xenon, and so on. Third, it has dust detectors. These instruments basically listen for tiny impacts. As grains of dust, tiny particles shed from the object's nucleus hit a detector plate. The instrument registers the ping. It can tell us how many particles there are, how big they are, and how fast they are moving. The information from these instruments could solve the object's deepest mysteries. The data from the plasma detectors, for example, could give us the exact chemical composition. We wouldn't just be guessing at elements based on their green glow, we would have a direct measurement. Most importantly, we could look for isotopes. An isotope is a different version or flavour of a chemical element. For example, there is heavy carbon and light carbon. The atoms are both carbon, but one has a few extra neutral particles. In our solar system, the ratio of these different flavours, say the ratio of heavy carbon to light carbon, is very consistent. It's a kind of chemical fingerprint for everything born here. If 3i Atlas's tail has a different ratio of isotopes that would be the smoking gun, it would be definitive, irrefutable proof that this object was not born in our solar system. It would be the chemical fingerprint of another star. This kind of accidental science has a history. In 1985, a spacecraft called the International Cometary Explorer, or IT, was repurposed and steered to fly directly through the tail of a comet named Giacobini-Zinner. It was the first time humanity had ever done such a thing, and it taught us volumes about what comets are really like. Then in 1996, the Ulysses spacecraft, which was built to study the Sun, had its own chance encounter. It unexpectedly flew through the tail of comet Hyakutake, revealing that comet tails were far, far larger than anyone had ever imagined. The tail Ulysses hit was over 500 million kilometers long. So when will we know if Hera and Clipper found anything? The answer is not for a while. This is what's known as opportunity science. It wasn't the main mission. The science teams for Hera and Europa Clipper are focused on their primary goals, asteroids and Jupiter's moons. The data from these spacecraft often takes a long time to be downloaded, processed, and analysed. It might be months or even longer before scientists have the time to go back and carefully comb through the data archives from that specific week in late October. They will be looking for a ghost in the data, a sudden spike in the dust counter, a strange reading on the magnetometer, or a burst of exotic ions in the plasma detector that shouldn't be there. It's digital detective work. We must be patient. But the possibility is there, hanging in the data banks waiting to be discovered. The first ever direct sample of an interstellar object might already be in our possession. We just don't know it yet. We have spent a great deal of time now sitting with this quiet visitor, the 3i Atlas. We've looked closely at its ghostly green glow, its powerful massive jets, and the strange chemical recipe it brought from its faraway home. But now let us do something different. Let's take a long step back. Let's zoom out in our minds past the orbit of Mars, past Jupiter, beyond the cold blue light of Neptune, and past the scattered belt of icy objects where Pluto lives. Let's drift out into the vast, silent and dark gulf of space that separates us from the other stars. From out here, 3 Atlas is not just a comet, it is a symbol. It is a messenger, and it is teaching us what our galaxy is really like. What then is the bigger picture? What is the true significance of this object? It is this Atlas is a physical sample. It is a piece of another solar system delivered directly to our doorstep postage paid by gravity. For all of human history, astronomy has been an act of looking. We are separated from the cosmos by an impossible gulf of empty space. We can look at the light from a distant star, we can measure its colour and its brightness, but we can never ever touch it. The universe, for all its beauty, has been a museum exhibit behind a very thick wall of glass. But 3 Atlas and the other interstellar visitors like it just smashed that glass. This object is not light. It is matter. It is rock and dust and exotic ices forged in orbit around a different sun. It is the universe reaching out and handing us a piece of itself. It is like standing on the shore of a vast dark ocean, an ocean we have never crossed. And suddenly a bottle washes ashore. It's not from another continent, it's from another world. We cannot read the label. We cannot know exactly where it came from, but we can study the bottle itself. And by looking at what 3 Atlas is made of, we can begin to paint a picture of the home it left behind perhaps millions of years ago. We can draw powerful inferences about its origin. First, let's look at its composition. As we saw, this object was overwhelmingly rich in frozen gases, what astronomers call volatiles. Specifically, it was loaded with frozen carbon monoxide and to a lesser extent carbon dioxide. These are not substances that freeze easily. Water ice, which is so common in our own comets, can form relatively close to our Sun, but carbon monoxide only freezes into a solid at incredibly low temperatures in the deep, deep cold. This tells us with great confidence that 3i Atlas was born in the freezing cold, dark outer reaches of its home solar system. It formed far, far away from the warmth of its parent star, in a place much colder and darker than the region where Earth was formed. It is truly a creature of the deep cold. Second, how did it get here? An object does not just decide to leave its home system and begin a journey of 1,000,000 years across the interstellar void. It has to be thrown. To be thrown hard enough to escape the gravity of its own star, it needs an immense gravitational push, a slingshot. In our own solar system, we know exactly what does that: giant planets. Jupiter and Saturn are our system's great gravitational bouncers. They are so massive that their gravity constantly tosses small comets and asteroids around like toys. Many are thrown into the sun, others are thrown into deep space, ejected from our solar system forever. So we can infer that the home system of 3 Atlas almost certainly has giant planets similar to our Jupiter, or perhaps even larger. This tiny speck of light is indirect physical evidence that giant Jupiter-like worlds exist around other stars, not just from the shadows they cast, but from the mess they make. There is another clue, a very subtle and beautiful one. Scientists used a technique called polarimetry. This is a special way of looking at the sunlight that scatters and reflects off the dust grains surrounding the object. It's less about what the dust is made of, and more about the texture and shape of the tiny particles. It's like feeling the surface of the dust using light as your fingertip. When they measured this polarized light from 3i Atlas, they found it looked surprisingly familiar. It was a very close match to the light scattered by objects in our own outer solar system. We call these the trans-Neptunian objects, or TNOs. This is the vast family of icy worlds that orbit in the darkness beyond Neptune, a family that includes Pluto and Eris. This is a fascinating piece of the puzzle. It suggests that the dust in that faraway system, the raw fundamental building material that came together to form 3i Atlas, is not so different from the dust in our own backyard. It implies that the basic physical processes that build planets the way tiny dust grains stick together might be quite common, quite similar from one star system to the next. But perhaps the most important lesson 3i Atlas has to teach us comes when we place it next to its fellow travellers. This is where the story gets truly interesting, because 3i Atlas was not the first. Before it we had 2 other confirmed visitors from interstellar space. First there was 1e Oumuamua. This was the Pioneer, the first one we ever detected, and it was a complete and total mystery. It was dark red, it was shaped perhaps like a strange cigar or a flat pancake, and most importantly it was tranquil. It showed no fuzzy glow, no tail, no activity at all. It didn't look like a comet. It didn't look like any asteroid we had ever seen. Enigmatic Scout. Then came 2i Borisov. This one was a deep relief to astronomers. It looked normal. It was fuzzy, it had a long, graceful tail, and its chemical makeup was very, very similar to the comets from our own solar system. It was the familiar cousin, the one who shows up and proves that our family isn't so strange after all. And then 3 Atlas arrived, and it blew everyone's assumptions out of the water. It was not silent and strange like Oumuamua, and it was not familiar and normal like Borisov. It was violently active. It was, as some scientists called it, a comet on steroids. It was immensely active, shedding more material more quickly than almost any comet we have ever seen. It was made of bizarre materials rich in those exotic frozen gases, but mysteriously lacking the water ice we expected. And it couldn't even survive a single trip around our sun. It shattered itself into pieces under the sun's gentle warmth, a task that our own comets endure thousands of times without complaint. So we have 3 visitors. One is strange and silent, one is familiar and normal, and one is violently active and chemically exotic. What does this diversity mean? It means that the universe is far more creative and far more varied than our limited imaginations had allowed. It means that planetary systems are not all built from the same blueprint. For a long, long time, our theories about how planets form were based on the only example we had, our own solar system. We assumed other systems would follow the same pattern: rocky planets near the star giant gas planets, farther out and a halo of icy comets in the frozen depths. These 3 visitors have shown us that this is a dangerously narrow view. It is as if we had lived our whole lives on a remote island inhabited only by birds, and based on this we wrote textbooks declaring that all animals in the world have feathers and wings. Then a boat washes ashore, and on it is a cat. We are confused. We update our textbooks. Okay, animals have feathers or they have fur. Then a second boat arrives and it carries a lizard. Alright, we say animals have feathers or fur or scales. Then a third boat, 3i Atlas, arrives, and it carries an octopus. We are forced to throw away our textbooks. We have to rethink our entire definition of what an animal is. Oumuamua, Borisov and Atlas are our cat, our lizard and our octopus. They prove that other solar systems are busy manufacturing an incredible variety of objects. Some systems, like the home of Borisov, might be just like ours. Others, like the home of 3 Atlas, might be very different, perhaps much richer in carbon and poorer in water. And some, like the home of Oumuamua, might be producing objects we don't even have a name for yet. The galaxy is a vast laboratory running billions of experiments in planet building at the same time. We are just now, for the first time, getting to see the results. This leads us to one final and slightly bittersweet thought. We have this object, we have these clues. We know it came from a cold place with giant planets from a system with dust like ours. But which star did it come from? We will never know. The journey was simply too long. 3i Atlas has likely been wandering the dark, empty spaces of the galaxy for millions, perhaps hundreds of millions of years. In that vast stretch of time, everything has moved. Our sun has orbited the centre of the galaxy. Its home star has also moved on a different path. The star charts of today are not the star charts of a million years ago. Trying to trace its path backward is like trying to find the single grain of sand that a great river picked up a million years ago, hundreds of miles upstream. The path is washed away. The galaxy is a moving, churning, dynamic place. This visitor, this piece of another world, is an orphan. Its past has been erased by time and distance, and so we are left with the message, but we will never know the sender. We can study it, we can learn from it, but we can never reply. We can never look up at the night sky and point to the star that sent it. This little comet which glowed so fiercely and died so dramatically in our sky is a ghost from an unknown star. And it leaves us with a profound and humbling reminder that we are part of a cosmic neighbourhood that is larger, more complex, and infinitely more surprising than we ever dared to imagine. The light from 3i Atlas is fading. With every passing day, our mysterious guest travels millions of miles further away, retreating from the sun's warmth and fading back into the deep cold dark. It is an echo of its arrival, but in reverse. The brilliant green anomalous glow that captured the world's attention is now dimming. The comet is for all intents and purposes walking out the door. This departure creates a profound and desperate sense of urgency for the scientific community. The window to study this object is closing. This is not a laboratory experiment we can repeat tomorrow. This is a fleeting, one-time-only event, and so a quiet, intense race against time is underway. Around the world, in the cold, dark domes of mountaintop observatories, astronomers are fighting to capture every last photon of light from this retreating visitor. This is the reality of the ongoing investigation. It is a coordinated global effort to ask all our remaining questions at once before 3i Atlas slips forever, beyond the reach of our most powerful eyes. The race against the fading light, this scramble for data, is happening on multiple fronts simultaneously. First, there is the simplest observation, photometry. This is the science of measuring brightness. Astronomers are meticulously tracking the object's fading light curve. We are watching how it dims. Is it a smooth, predictable fade like a simple rock tumbling away into the darkness? Or is it still flickering? Are there tiny, unexpected bursts of brightness? The last gasps of activity as small pockets of trapped gas or ice finally see the sunlight. By tracking its brightness, we are essentially taking its pulse. We are listening to its fading heartbeat, trying to understand the engine that powered it for so long. Every flicker, every deviation from a smooth curve is a clue to the physics of this strange body. At the same time, other telescopes are engaged in spectroscopy. If photometry measures how much light, spectroscopy asks what kind of light. The faint fading light from 3i Atlas is captured and split into its component colours, a rainbow or spectrum. In this rainbow, scientists are hunting for chemical fingerprints. They are searching for the signatures of minor chemical species, the trace elements that might have been hidden by the object's main bright emissions when it was closer. Are there complex organic molecules, the building blocks of life, hiding in that faint glow? Even more profoundly, they are hunting for isotope ratios. An isotope is a slightly heavier or lighter version of a common element. Our own solar system has a very distinct fingerprint of these ratios. For example, the ratio of heavy water deuterium to regular water is a known quantity here. If the isotope ratios on 3i Atlas are different from our own, it is the final definitive proof of its alien origin. This is cosmic DNA testing, and it is being performed on the faintest of light hundreds of millions of miles away. While the spectrographs are tasting the light, other instruments are trying to get a picture. This is the challenge of high-resolution imaging. At this distance, 3i Atlas is an unresolved point of light, a single dot. We cannot see its shape, but we are not trying to see the object itself. We are trying to see what is around it. We are looking for structural changes in its coma, the vast, dusty, gassy cloud that surrounds it. Are the massive jets that we detected earlier, the very jets that fueled its green glow, still firing even weakly? Is the coma lopsided, suggesting material is still spraying out from one side more than another? Using advanced techniques that correct for the blur of Earth's atmosphere, astronomers are straining to capture the ghost of the object's activity. Finally, there is the precise work of astrometry. This is the science of measuring exactly where the object is in the sky. Every single observation every night helps to pin down its location with almost unbelievable precision. This is crucial because of the NGA, the non-gravitational acceleration. The object is still not moving quite right. It is still being gently pushed by an unseen force, presumably the last remnants of its outgassing jets. By refining the NGA parameters, that is, by tracking its path deviation more and more accurately, we can finally work backward to solve the mass puzzle. If we know exactly how hard it is being pushed, we can calculate the force of the jets. And if we know the force of the jets, we can finally estimate the true mass of the object. We can finally answer how something that appeared so massive could be moved so easily, looking backwards and forwards. This intense observational sprint is not the only work being done. There is a second, quieter hunt happening on computer servers. Scientists are mining data archives. They are scrolling through petabytes of old sky surveys looking for pre-discovery images. They are searching for old, overlooked astronomical photographs from 5 or 10 years ago, where 3i Atlas might have appeared as a faint anonymous smudge in the corner of the frame long before anyone knew it was special. Finding even one such baby picture would be revolutionary. It would give us a baseline. It It would show us what the object looked like before it flared up, helping us understand its long cold journey through interstellar space. And in a broader sense, the investigation involves waiting. We are waiting for data from the next generation of space exploration. While missions like the upcoming Hera probe to an asteroid or the Clipper mission to Jupiter's icy moon Europa are not going to 3i Atlas, they will teach us invaluable lessons about how icy bodies behave in our own solar system. By understanding our own celestial neighbours better, we build better models to understand our interstellar guests. This all points to a brilliant future. The sense of urgency we feel now, this frantic race against the dying light, will soon become routine. High on a mountaintop in Chile, a new revolutionary eye on the sky is coming online, the Vera Rubin Observatory. This is not just another telescope, it is a discovery machine. Its vast mirror and enormous camera will scan the entire visible sky every few nights, creating a motion picture of the cosmos. And in that movie it will catch the interlopers. It is estimated that the Vera Rubin Observatory will discover dozens of new interstellar objects every single year. Think about that. We went from one Oumuamua to two Borisov to this profoundly strange third visitor. Soon we will have a catalogue. We will have a population. 3i Atlas will no longer be a complete anomaly. It will perhaps be the first example of a whole new class of object that we never knew existed. The investigation of 3 Atlas is not just teaching us about one strange traveller, it is preparing us for the coming flood. It is the dress rehearsal for a new era of astronomy, an era where interstellar is no longer a novelty, but a new rich and fascinating frontier. We have travelled so far together following this incredible visitor from another star. We have watched its strange green glow, we have puzzled over its impossible speed, and we have tried to understand the chemical mysteries it carried from its distant unknown home. And now our journey with 3 Atlas is coming to an end. It is now fading, a tiny speck of light disappearing back into the infinite darkness from which it came. It is moving so fast that our solar system can no longer hold on to it. It is returning to the deep ocean of interstellar space. But just because it is leaving, that does not mean the story is over. In fact, for us, the real story is just beginning. A great mystery does not end when the evidence disappears. The evidence is simply the first spark. The mystery lives on in our minds, in our laboratories, and in our theories. 3i Atlas did not give us a neat and tidy package of answers. It did not solve the riddles of the universe for us. Instead, it did something far more important. It left us with profound, beautiful, and challenging questions. These questions are its final gift to us. There is so much we still do not know. We have the data that suggests this object lost an incredible amount of its own body. The number we calculate is almost 10%. Can we truly grasp what that means? Imagine a mountain of rock and ice kilometers wide, traveling faster than anything we have ever seen. And in just a few short weeks, as it swung around our sun, 1/10 of that entire mountain dissolved. It simply vanished into gas and dust. Is this number real? And if it is, what force could possibly do that? Was it a catastrophic explosion from deep within the object as frozen gases trapped for billions of years finally found a crack and burst into the vacuum? Was it a rotational breakup, the object spinning itself into a frenzy faster and faster until it started to fling pieces of itself into space? We just don't know. This single question, the mystery of the missing 10%, challenges everything we thought we knew about how comets and asteroids behave. And what about its spin? How was it turning? This seems like such a simple detail, but it holds the key to its nature. Think of a spinning top. When it is spinning fast and perfectly, it is stable and strong, but when it wobbles, it is unbalanced and chaotic. We tried to watch 3i Atlas looking for a steady pulse of light, the regular blink that would tell us it's day. We never found one. The data was confusing, chaotic. This might be because the massive jets firing from its surface were not balanced. They were acting like wild, unpredictable rocket engines pushing the object, making it tumble and twist. Was it spinning fast? Was it spinning slow? Was it tumbling end over end like a broken shard of rock? Without knowing its spin, we cannot truly know its shape, its history, or its strength. We were trying to understand a dancer, but we were only allowed to see a blur of motion. Then there is the question of its tail, its magnificent green coma. We saw it, but we also saw it change. Night after night, the structure of that glowing cloud was different. The jets that fed it were not constant. They would flare up, becoming intensely bright, and then they would die down again as if a switch was being flipped. This tells us the surface of 3i Atlas was not a simple uniform ball of ice. It must be a complex world. It must have active zones, places where the ancient ice was exposed to the sun and other places perhaps vast plains of dark insulating dust that remained quiet and cold. Why? What created this landscape? Was it the scar of an ancient collision, or was this just the way it was born? We only saw it for a few months. We have a few precious snapshots of a dynamic living object, but we do not have the whole film. We missed the beginning of the show, and we are missing the end. And what did our greatest instruments, our powerful eyes in orbit, finally tell us? Did the spacecraft and space telescopes solve the riddle? In a way, they only made it deeper. They confirmed the strangest parts. They used their incredible power to verify that yes, the water was missing. Yes, the nickel was present. Yes, the green glow was real. They gave us the precise ingredients, but they could not tell us the recipe. They could not tell us why. These profound questions are where we are left. And perhaps this is the most exciting place to be. If this journey we have taken pondering these deep cosmic questions has brought you any sense of wonder or peace, I would be so honoured if you would join this community. You can subscribe to the channel so that we can continue to explore these mysteries together. If you like, you can also tap the notification bell. That way you will always know when our next voyage is about to begin. I would truly love to hear your own thoughts. Please leave a comment below. What single part of this entire story, the mystery of 3i Atlas, did you find the most fascinating? Was it the colour? Was it the speed? Was it the fact that it came from so far away? And finally, if you know someone else in your life who also looks up at the night sky and feels a sense of awe, or someone who just needs a quiet moment to relax and think, please feel free to share this story with them. These great cosmic stories are always better when we experience them together. This right here is what real science looks like. It is not always clean. It is not just a list of facts in a textbook. Real science is messy. It is confusing. It is full of passionate debate and disagreement. It is controversial and it is thrilling. It is the sound of the human mind stretching to reach for something it does not yet understand. For Atlas is leaving us. It is falling back into the cold, silent darkness, returning to the interstellar void. We will almost certainly never see it again. It passed through our solar system like a ghost, a messenger from an unknown shore. But the questions it raised will not leave. They stay right here with us. They will echo in the halls of universities and in the quiet of observatories for years, maybe even decades to come. They will inspire new theories, they will drive new missions, and they will inspire a whole new generation of explorers to ask, what else is out here? The object is gone, but the puzzle it left behind remains. And in the end, the puzzle is the real gift. Thank you for spending this time with me. Until our next journey.